Alright everyone, in this video we're going to start taking a look at how we actually go about to start implementing some of our tree algorithms that we discussed. So in the last video we kind of talked about a little bit what a tree is, what some of the different variations of trees are, and some of the rules associated with them. And one thing we really looked at was the fact that trees are self-defining data structures such that a single tree is made up of many smaller subtrees inside of the tree. And also B, we looked at how we can go about to traverse a tree and visit all of the nodes in the tree, such that our normal linked list traversals aren't actually going to allow us to cover all of the nodes in the tree. So we then talked about how we kind of combine the two aspects, that we can't just linearly traverse a tree, and how they are self-defined data structures such that we can use some recursive functions to actually go about and traverse the trees for us. And the three functions we talked about were basically an in-order traversal, a post-order traversal, and a pre-order traversal. So these are three recursive methods that we can use in order to actually go about and traverse the tree and visit all of the nodes in the tree, even though it's a non-linear data structure, right? We're going to have some root tree that's going to have a couple children, that's going to have a couple other children, so on and so forth, and we're going to have all of these different levels in our tree. So these three traversals are really going to allow us, excuse me, to visit all of the nodes in a recursive manner. And we also said how, because a tree data structure is abstract, we can go about and implement it using an array or a linked list. It kind of depends up to your implementation. The first bit of code we're going to look at is basically just us trying to code up a binary tree with our three traversals using an array. Okay, so we'll look at that code first. Just as a reminder of the pseudocode for our traversals, we kind of had, what we had? So we'd have a pre-order traversal, and inside of that traversal, we would basically print the node, then we would recurse left subtree, and then we would end up recursing the right subtree. And all of our other traversals were basically just some variation of these three steps. Ooh. I don't know why my screen got smaller. Go back. What the... Try this one more time. There we go. Alright, so an in-order traversal would be the exact same steps. It would just be that the order that those steps are done in would be a little bit different. Alright, so in order, we would actually go about, we would recurse the left subtree, then we would print the node, and then we would recurse the right subtree. And in the case of a post-order traversal, we would go out and we would end up recursing the left subtree first, then we would recurse the right subtree, and then we would print out the node. So all three of these methods of going through our tree are going to visit all of the different nodes. They're just going to print out the nodes in different order. That's kind of the idea behind it all, that we want these different orders, and really these different traversals kind of tie in with how certain mathematical expressions are evaluated, which, if we get time, we'll take a look at that later on. So because we're doing this in an array, remember, if we store a tree in an array, we basically start at some node with some n index into the tree, and then in order to get that parent's left child, we would need to go to index 2n. If we want to get to that node's right child, we would go to index 2n plus 1. So we have this relationship that we're going to use to basically tell us whether we're going to the left or to the right. And we're also going to notice, as we write up this code, that the actual code that we're writing to actually traverse our trees is going to look strikingly similar to the pseudocode. That's one thing to note about recursive algorithms. They usually tie very closely to the pseudocode that you write because of the fact that recursion basically differs in iteration in that we don't necessarily do a certain set of steps every time, we're just following a certain pattern which leads itself to solving our problem. And we'll see this once we write the code. So if we just look at kind of our boilerplate program that I have written up here, we have our normal include IOStream using namespace. I define a constant size, which we're going to use to control our array size. Then we're going to define a constant root value. Root just tells us where the root of our tree is, and the root of our tree is always going to start at index 1, so we're going to kind of forget about index 0, because if we used 0, our math would not work out to get to our left and right childs, right? Because 2 times 0 would always be 0, 2n plus 1 would be 1, right? Which would throw everything off. So we're just going to start at 1. Then we go ahead and we have our class definition. So with our binary tree, we just have our tree constructor. Then we have our 3 traversal prototypes. We have in order, post order, and pre-order. And each of those functions is going to take, excuse me, an integer parameter. And that integer parameter is basically going to be the index into the array that we're going to use to start to traverse our tree. And then, of course, we just have the actual array that we're going to use to store our information. And that array is of size, effectively. So we go down to our constructor. Nothing too serious here. We just have a loop that's going to fill our tree with some numbers. Now note, because we are building our tree in an array, we can just fill our array left to right and everything's going to work out correctly. Because remember, I had mentioned that in binary trees we need to build a complete tree such that we fill the first level completely left to right, then the next level completely left to right, next level completely left to right, so on and so forth. And by using an array, this is effectively taken care of for us because of the way that the array is filled out and how the indexes in the array relate to the parent-child relationship. So that is all just going to work out for us. We can just fill our array with numbers. And then we can come down and start looking at, okay, how do we actually go about writing these functions? So we have our in-order, post-order, pre-order functions. We're not going to worry about in-order or post-order yet. We're actually just going to do our pre-order function first. So I'm just going to put that up there. So let's look at what our pseudocode for pre-order is. I'm going to bring this, except I didn't get it all. Let's bring this down here. Okay, so our pseudocode basically says that we need to print the node, recurse to the left subtree, and then recurse to the right subtree. Alright, so this basically tells us exactly what we need to do to get a pre-order traversal working correctly. So first things first, according to our pseudocode, is we need to print the node that we're currently on. So if we wanted to print the node, we could do cout tree index. Right? Because tree is our array that we're storing all of our nodes in, and then index, which is passed into the function, tells us what index into the array we're currently at. So that's basically what node in the tree are we looking at. So we would call this function with something like tree.preorder and then, start at node 5 or start at root, right? So that would get passed into this function, which would tell us, okay, print out that index. Okay, the next thing we need to do is recurse to the left subtree. Right, so this is the part where everybody's kind of thinking, okay, I don't know how this necessarily works or why this works. So if we want to recurse into the left subtree, we just need to kind of tear apart our problem a little bit. First things first, we know we need to recurse. We're going to recursively call our function, right? So we already know that the function we need to call is preorder because it has to be recursive. If you called some other function here, it wouldn't be recursive and you'd get incorrect answers. And we also know that we are looking to recurse into our left subtree. Excuse me. So our left subtree is going to be whatever is basically at 2n to our current node, right? According to our tree. If we want to get to the left child, and because a single node in a tree is also a tree, this is an overloaded term. To get to not only the left child, but also the left subtree, we need to go to node 2n. So to go there, all we would need to do is call preorder, and then we would pass it basically 2 times whatever node we're currently on, which is index. All right, so that's recursively going to call preorder going to the left. And we need to remember every time we hit this line, our current instance of preorder basically freezes and another preorder function is basically created and starts running. So if we call preorder and pass it 2 times index, this instance of the function freezes and another instance of preorder gets created off to the side and starts running at the top again. So it'll call preorder, it'll print off whatever's at 2 times index, and then that function will call preorder and go to 2 times whatever that index is, so on and so forth. And we'll keep going down the chain until we stop or hit whatever base case, in which case we start coming back up that chain in a backwards fashion, where each instance of the function keeps executing the code after that where that recursive call was at. And we'll look at some code here in a minute that kind of demonstrates that a little bit better for us. So after we recurse the left subtree, we need to actually recurse to the right subtree. And if we want to get to the right subtree or the right child, remember a child is in of itself also a tree because a single node is a tree in this context. So if we want to go right, we're going to use 2n plus 1. So in order to go to the right tree, we would just call preorder and do 2 times index and then plus 1. And that would then go to that node and print it off the value, and we would go to the right from there and then to the left, and it just creates this whole chain and tree of actions that happen. So right there, this is a preorder traversal. It is 3 lines of code, and it matches almost exactly to its pseudocode. Right? The code for these things is not that difficult to write. It's just kind of wrapping your head around what exactly is happening that's going to cause the problems. So what we should do now is just compile this code, and let's see what happens when we do it. So it compiles. If we run it, we get a segmentation fault. So now the question is, why did we get a segmentation fault? And that answer for why we will get a segmentation fault goes to the way we structured our recursive function. Okay, what's going to happen if we just call this function the way it is? The way this function is currently written, it's going to just infinitely recurse until we run out of memory space and we get that segmentation fault, right? There's nothing that tells this function when it should stop calling itself. All right, so we're just going to basically infinitely loop here and get into this pattern of call a new pre-order function, print something out, call a pre-order function, print something out, call a pre-order function, print something out, so on and so forth, because we have no base case. We have nothing in here that says when the function should quit. Right? Every recursive function you write needs to have some case in it that basically says, hey, stop running, you've reached the end of your problem. Right? So for us, our base case is basically when our index has gone past the end of our array. So if we want to check that, what we can do is if index is less than our size, right? Because our size says how big our array is, and index is the current node that we're trying to access inside of our array. So if index gets bigger than size because of one of these calls where we double it, we know we want to stop. So for that, just wrap this in quotes real fast. And then we'll compile it again. And we'll run it. And this time, we get our traversal. Right, so we get our 1, 2, 4, 8, 9, 5, 3, 6, 7 traversal. Now the question is that a correct traversal? You know, how are we going to check this? So to check this, it's going to be pretty straightforward. And it will require a little bit of drawing. To make it a little quicker and easier to draw, we're just going to make our array a little bit better, or smaller, I should say, not better, and we will run our program again. Alright, so our pre-order traversal is basically 1, 2, 4, and 3. So with that, we know, I should have had this. So we already know that our array is basically going to have 4 elements in it. Get this plugged in. Come on. Not sure why that's not working. There we go. Okay, so our array is basically going to look something like this. We'll have a 5-element array, so index 0, 1, 2, 3, and 4. And we're going to have the numbers 1, 2, 3, and 4 inside of that array. Remember, there's nothing in 0 because that would mess us up. So our tree is basically going to look something like 1. I don't know why this is so laggy. 2, 3, because remember our relation, we're at index 1, so its left child is at 2 times n, which is 2. Its right child is at 2 times n plus 1, which is 3. And then 4, which is 2's child. Right, because to get to the left child, you'd go to 2 times n, so 2 times 2 is 4, go to index 4, that's our child. So if we wanted to do a pre-order traversal of this, remember the whole recurse, you print the value, recurse left, recurse right. The other way to remember looking at how to doing this was basically you draw the track around your tree, and if you're doing a pre-order traversal, whenever you get to the left of your node, you print it off. So we'd have 1, we'd have 2, we'd have 4. And then we'd come back up here following the track, and we'd have 3. So our pre-order traversal should be 1, 2, 4, 3, which is exactly what our program spits out. So we know our pre-order traversal is correct. If we really wanted to see what was happening in here, we could, or see how many times our recursive function is called, we could just print this out. We could say cout and just print a message that says, hey, we entered our recursive function. Alright, so you can see our recursive function gets called 1, 2, 3 times at least, or I guess it'd be 4. We're just short one print message. But we'll look at a bit more explicit example of this recursion being called in just a minute here. Okay, so once you have one of these traversals done, the other traversals should be pretty easy, right? Because they're all doing the same thing, they're just doing them in different orders. So if we wanted to change this up, we could just copy this code and we'll bring it down here. And in our in-order traversal, remember, instead of printing the number first, we traverse left first, then print the number, and then traverse right. So in which case we could save this code, bring back our terminal, we'll run it, and now we see our in-order traversal is supposed to be 2, 4, 1, and 3. So if we look back at our little track example here, if we follow our track, remember in an in-order traversal, as we follow it, once we get below a number, we actually print it off. So we would have 4, 2, 1, and 3. Alright, so that would be our in order, which is exactly what we have. Or nope, maybe because I forgot to rename our functions. The dangers of copying and pasting code right here. What is going on? I don't know why I can't highlight anything right now. In order. Now we'll go back. Maybe. This virtual machine is not happy currently. Okay, I will be back in 1 second, so here's a cut in the video while I try to get this fixed. Alright, we're back. Just had to restart the VM quick. So now, after that, I've renamed the recursive function calls to actually call the right function. Now we should be in better shape. So, G++, bintree array, run it, and now we should get the 4213 that we expected for our in-order traversal. And for our post-order traversal, it's going to be just the same thing again. Just reorder everything. So the last thing we do is print off the value of the node that we're on. And this time, remember to rename the functions to call the correct functions. So there we go. And now when we compile it, we should get our post-order traversal in there as well. So our post-order traversal comes up 4231, which we can go and check over here. Remember, with our post-order, we follow the track. When we get to the right side, we mark it as printing. So 4, keep following track. We follow the track, we get to the left of the 2, print it off, 4, 2, follow the track, get to the right of the 3, 4, 2, 3, and 1. And there we go, there's our post-order traversal. which is exactly what we expected. Okay, so there is basically our three traversals, and notice they're not, anything too serious or too crazy. The code is not that bad. It's just wrapping your head around how this recursion works and how we're jumping around the tree. Alright, so to make things a little bit more explicit to what's going on, I took this same program and I just actually ended up adding in some printing statements to be like, hey, here's the start of a recursive call, here's the end of a recursive call, and just try to demonstrate that a little bit better. What did I call it? That's the next question. Trace. So if we look at that, it is the exact same code again. The only difference is now for each recursive call, we print off a message that says, hey, we're about to enter a recursive function, and we use the index to say what function is being called or what number is being called. And then we print off another message that basically says, hey, we just left that recursive call. So we can kind of see this chain of new recursive calls happening every time we go through one of these traversals. So we can see where one function basically starts, all the recursive calls that happen inside of that function, and where that original function actually ends, which is kind of cool and makes it a little bit easier to see. So if we compile that quick, and we'll run it. So now we just get all of this stuff. Okay, so for instance, here we have our in-order traversal. Okay, so here we have it saying we're about to enter our left recursive call, and we're calling it from index 1, right? So we're calling this function from the very first node in our tree or our root tree. Okay, then it says we're calling left recursion again. This time we're from index 2. Okay, so we call it. We must hit the bottom of the tree because now it says we're exiting the left recursion from index 2 or from node 2. And then we're calling the right recursion from 2 and exiting our right recursion, which falls directly in line with what in-order traversal is doing. Okay, then it says we're finally exiting left recursion from 1. So we had all of these steps happen inside of this first recursive call. Where's in order? There's in order. Right, so all of these functions got called from this one original recursive call in our in order function, right? So we printed the message entering left recursion from 1 here, and then these other 1, 2, 3, 4 lines got printed all from this recursive call because we make this call, which makes other calls and other calls and other calls, and it keeps branching off. It's all kind of this inception thing, right? Then eventually we end up coming back after we've run all that to where we originally left from, right? Which is this exiting left recursion after all of the calls that were created from this one recursion return. Then we start running the rest of it. Alright, so here we have entering right recursion from 1 and exiting left recursion from 1, at which point the whole chain kind of stops, right, because we hit our base case. Alright, so you can see how these two match up with this guy up here. Alright, and then everything in between there is some other recursive call. Alright, the whole idea of recursion is that we basically make these chains of calls that then come back up, basically. Wonder if I can take a screenshot. Probably not. Or paste it in here. Let's just see here. New. That's a bummer. So if we had our function that was basically print call left, and call right. Right, so we would print some number. So let's just say we printed a 3, and then we'd end up calling to our left recursion. Right, when we call to our left recursion, we basically end up, this is not the best program for this because yeah, there we go. That's not what I want. Where is the selection? There it is. We basically end up calling the same function over again from our original function, right? Which just basically creates another copy of it, right? So that calls that function, and nothing else happens here for now because now we fall over to this function. So we would print off some number, so we might print off, 4. Then we'd end up calling left again, which would create another copy and make another link in this recursive chain. At which point we'd come down here, we'd call print, so we might print off a 7. We'd call left again. So we'd have another copy of the function down here. At which point we might print our number. And now let's say we really have nothing to call left on. Let's say we hit our base case. Right? If we hit our base case, then this function would just come back, basically having done nothing. We'd call our right function, which if we hit our base case again would do nothing, which means we then basically reach the end of this function call. At which point we come back up to the point from which our function was originally called, which was right there. So now that we've come back, we can call the right function. Right, so our right function might basically do the exact same thing again. We just have another copy of the function running, which would probably print some value. And then if it had to call left again, it would call left. But let's say that did nothing there and we returned. Then we'd call right, which did nothing and returned. So we would then come back up to the original point from where this function was called, right? Which takes us to the end of this function. Once this function's finished executing, it goes back to where it was originally called from, which was from our call left here, which then brings us to being able to call right in this function, which again starts off just this another chain that we can go around walking around. Right, so this would call him down here, which would call 9, or we could print 9, we could call left again in a whole nother chain, but for simplicity we're just going to say that returned nothing, that it had nothing to do. We'd call right, which did nothing, so we reached the end of our function, and we would go back to from where we originally started, which was our call right, and there's nothing else to execute, so that function returns. And we'd go back up to our left, and then we would again call right, which would follow the same pattern over and over again. Right, so it's easy to see here how with one recursive call, we all of a sudden get this very big, long, complicated call chain. The important thing to remember is that when you call a recursive function, you're just calling another copy of your function, which is going to do the same thing over and over and over again. Right? And then once the functions have hit their base case, or the most recursive in-depth function hits its base case, it's going to start returning back to where it was originally called from. Right? So this allows us to bring values back up. We kind of dig down really deep into a hole, and then we bubble what we want back up through this calling chain over and over again. Okay, so if this is still confusing, make sure you check out this code, our binary tree trace code, which kind of lays out how the recursive calls are being made, and try to pair it with drawing out the whole chain. Okay, print or pre-order left creates another copy of the function, and we keep following this case until we hit our base case and keep bubbling back up. Okay, so try to work on that. Make sure if you have questions on recursion that you get a hold of me and I can help you out with it. Okay, so in this code, this was basically all of our tree traversal code that we need to worry about. Overall, that is how we traverse our trees. Now granted, this is just a array representation. Remember, we had also discussed that we could do this with a linked list representation of our trees. All right, so if we wanted to do that, we are basically going to end up, or I should say, if we wanted to actually create a tree with a linked list, or using nodes for a linked list, we're basically going to have to modify our structure a little bit to allow for this multi-level hierarchy. Right? Before we were, have a linear list, we would add at the front, we'd add at the back, we could add in the middle if we wanted to, but everything always pointed to every other thing in the chain eventually. So now, to accommodate this hierarchical structure, we're basically going to need to add some pointers to our structure representing our nodes to basically point at the left and the right children of the tree. So it's kind of a take on the doubly linked list, actually. So the struct that we're actually going to use to build our trees is going to look something like this. We're going to still have our value that we would normally have, and then we would have now 2 pointers to our left and our right child. Very similarly to how a doubly linked list would have a pointer to basically the previous and next nodes. Now we just have a pointer to the left and right. But again, this is not going to be a linear structure. Right, so really our tree is going to end up looking a lot like this, or logically, this is how our tree is going to get laid out in memory. We'll have some root node that's going to be having a pointer to its left and pointer to its right, which will in turn have other nodes with pointers to the left and to the right, etc., etc., etc. So this is kind of the structure we're going to be building off of for the rest of our trees. So if we want to just take a brief look at what this might look like in code, I have a small example for us to start working with. Again, this is just going to be a very partial example because your assignment is going to be to actually build up a full tree with a linked list. Oh, come on. So if we take a look at what this is going to look like, we can define our tree node. All right, so we have our value, we have our left, we have our right, and then we have our class definition. We have our constructor, we have our partial insert function, we have our pre-order function, and then you're going to notice I have 2 other functions down here as well. One called partial insert helper and one called pre-order helper. You're going to find that when we're dealing with recursively going through linked structures, so structures that involve using linked lists and jumping through linked lists and modifying linked lists, it usually helps to do each function in kind of a pair. So you have a public function, which is going to be what's called by the actual user to actually kickstart everything for you. And then you have the actual recursive function that does the work. So our wrapper function will call the recursive function with the extra information it needs to actually go about and do its thing. Right, extra information that the user of your class might not actually have or might not actually know. So we have the partial insert helper function, which is going to insert a node into the tree for us. And we have our pre-order helper function, which is going to help us actually traverse the tree in a pre-order fashion. And then of course we have our root pointer, which holds everything for us. All right, we have our constructor, which just basically says our root is null, there's nothing in there. And then we start actually using our functions. And once we talk about our next type of tree, these functions will make a bit more sense, but for now, this code is just going to be out there for you to help you kind of structure your linked binary trees. This code is going to be specific towards what's known as a binary search tree, which we're going to talk about in the next video. All right, but I just wanted to make you aware of this code. We'll actually look at this code in closer detail in the next video. So for now, that's all. We will catch you in the next video for binary search trees.